In this tutorial, we will use definite integration to find areas under curves. Look at the description. You need to be able to use definite integration to find areas under curves. Look at this curve. Y equals f of x, and we represented the area with letter A as a function a of x. Then, for any curve with equation y equals f of x, you can define the area under the curve and to the left of x as a function of x called a of x. As x increases, this area, a of x, also increases, since x moves further to the right. Let's see an example together. We have the same function and graph as above. However, we add a small value to x, and we defined it as delta x. This line is y equals to f of x. So this is y. Since we added x by delta x, then the area will also increase in a small value. If you look at a small increase in x, say delta x, then the area increases by an amount delta a. As we said, whenever the x increases, thus moving to the right, then the area will also increase. So if x increases in a small amount, then the area will increase in a small amount. This amount is delta a. Delta A is all of this area, which is area x plus delta x. So it is A for x plus delta x minus a of x. Subtracting the small area from the large area will result in the small amount of change in the area. This extra increase in the area delta A is approximately rectangular and a magnitude of y delta x. If you look at this extra part, here you can have a rectangle and ignore the tiny part above. So you say that delta A is a rectangular increase, and we know the area of the rectangle is length times width. Length is y and the width is delta x. As we make delta x smaller, any error between the actual area and this will be negligible. So this will become more of a rectangle as the small area here decreases. We said that delta A is approximately y delta x. Then delta A over delta x is approximately y. Y is the function of this curve. Let's continue. If we take the limit of delta A over delta x, a delta x goes to 0. We will have differentiation. That means we have a derivative delta A of delta x is y. Remember that the delta x is a small amount, so it will be very close to 0. Now, if you know that delta A over delta x is y, then to find a, you have to integrate, giving a is integral of y dx. So we can say the following. Delta A, if we cross multiply, it will be y times dx. So to know the exact value of the area, we integrate both sides, and this will result in a is integral of y dx. This is important for the application. In particular, if you wish to find the area between a curve, the x-axis, and the lines x equal a and x equals b, as you can see in this figure, if we have this curve, we don't want the entire area to the left for some value that is specified for x. We want the area that is specified between the x-axes. This is the x-axis. Between the lines, x equals a and x equals b. We only want this area here. This area is integral of y dx, and it is a definite integral, starting from x equals a to x equals b, where y equals f of x is the equation of the curve. So here we have a function that contains x. We work like we did previously. The only difference here is that we will obtain a value that defines an area. So since it defines an area, it cannot be negative, and it cannot be 0 since the curve is higher than the x-axis.